In this section, we're going to be introducing two concepts. And those two concepts are referred to as linear approximations and differentials. I'd like to start with the linear approximations. So let's say, for the sake of argument, that you are measuring two sides of a right triangle. You get that one of the sides is 1.1 centimeters, and that another side is 1.7 centimeters. Your job is to, as accurately as possible, determine how long the hypotenuse is. Oh, but you just broke your ruler and you can't use it anymore. Oopsie poopsie. So for just a moment, we're going to refer to that as C, as in A, B, and C for the three sides of a right triangle. We know that they are related using the Pythagorean Theorem. A squared plus B squared is equal to C squared. So that'd be 1.1 squared plus 1.7 squared is equal to C squared. Now, without too much difficulty, we could probably get the first two squares without too much of a problem. Combining those numbers together, we're going to get that C squared is equal to 4.1. Or that C is equal to the square root of 4.1. Now, this is where things are going to get a little more complicated because 4.1 doesn't have a particularly nice looking square root. However, I do notice that 4.1 is pretty close to a number that does have a nice square root, and that number would be 4. So would it be true that the square root of 4.1 would be a little bit bigger than 2 in the same sense that the square root of 4 is equal to 2? So, which is approximately bigger than 2? I guess the real question becomes, how much bigger than 2? Well, here's where we're going to throw some calculus in here. Imagine that I'm talking about y is equal to the square root of x. Graph of this function looks approximately like this, half a sideways parabola. We got 4 right here, and we got 4.1 pretty much right next to it. Now, getting the square root of 4.1, that's going to be awfully complicated. So what we're going to do is come up with an approximation based off of the fact that 4 has a really nice square root. The other thing I'd like to point out is that if we were to do basically the first thing that we've done with all of these, which is draw in a tangent line, oh boy, that's not a very good line, but we're going to go with it. That near, we'll put quotation marks around that, near x equals 4, the tangent line is approximately equal to the actual function. The reason I bring this up is because tangent lines tend to be a little bit easier to work with, usually something of the form y equals mx plus b. So here's what we're going to do. Find the tangent line at x equals 4, and then plug in x equals 4.1 to that model. Now, because it's an approximation of the original function, and because it's a tangent line doing it, this is where the term linear approximation comes from. So approximating an actual function using a line. Now, in order for us to do so, we would first need to know what is the ordered pair associated with this. If I plug in x equals 4 to our function, we'll get y equals the square root of 4, that would be 2. Additionally, we're going to need the slope of the tangent line, so we're going to need a derivative. Now, as we've been doing since last chapter, anytime we're dealing with a square root, it's going to be better off to refer to it as a 1/2 power. This is so that we can use the power rule as a derivative shortcut. Now, rewriting this back in the form of a radical, that would be 1 over 2 square roots of x. We're interested in the slope of the tangent line evaluated at x equals 4. So we'll go ahead and plug in x equals 4. We're going to get 1/4. Now, with that in mind, if we take all of the necessary information and plug it into the point slope form of a line, which is that the slope is 1/4, and that the ordered pair is 4, 2. Point slope form of a line says we'll do y minus y1 is equal to m times x minus x1. Moreover, if we wanted to simply solve for y, we could say that y is equal to 2 plus 1/4 of x minus 4. So this would be the slope of the tangent line at x equals 4. Now, what the linear approximation argument is saying is that near, put that in quotation marks again, near x equals 4, the square root of x is going to be approximately equal to 2 plus 1/4 of x minus 4. So the actual function is approximately equal to the equation of the tangent line. So now let's plug in x equals 4.1. So the square root of 4.1 is going to be approximately equal to 2 plus 1/4 of 4.1 minus 4. Well, that would be 1/4 of 1/10. 1/4 is 0.25, so 1/4 of a tenth would be 0.025. Now, the reason I put quotation marks around the word near is because it's all relative. The closer you are to x equals 4, the better the approximation is going to be. Would this approximation work well if I were plugging in, say, x equals 6? Well, it's probably not as good an approximation. Whereas you could say, what if I'm plugging in like x equals 100? Well, this would be terrible then. Now, just to verify how good our answer is, I would like to grab the calculator and say, how much is the square root of 4.1? Calculator tells me that that's about 2.0248. We got 2.025 without even having to resort to a calculator. I would say we just did pretty well. In the next video, I'm going to generalize this as we talk about the linearization of a function.